Okay, let's get started then. Welcome to the first distinguished lecture in this year's VV program. We're very happy, we're very fortunate to have Prabha from Mandayam from IIT Madras. She's one of the foremost experts on quantum information and computing in our country. And so Prabha, in fact, I just found out that she was like you, a visitor, summer visitor to TIFR many years ago. She was a project student here, and then after that, she went on to get a PhD from Caltech in quantum computing. And after some stints at CMI, IMSC and CMI, she is now at IIT Madras. So her interests are in quantum information and quantum computing, and we'll hear more about it. So without any further ado,
thank you, Vinod, Kavita, and all the organizers of this Vidyan Vidushi program. As Vinod mentioned, it's really lots of old fond memories. I did indeed spend an entire summer here, almost 2 months, like I was saying, many years ago. The number shall go unspecified. But it was a very formative experience for me to sort of have this kind of a residential program at a science institute, sort of be immersed in talks, research, widespread across many areas, not just one. So, of course, my background is in physics. But as I was telling them just now, this room, in fact, I remember listening to a lecture by Professor Dani, who's a mathematician now retired from TIFR, but on transcendental and irrational numbers, right? So these are all sort of experiences which I think, I speak from the wisdom of age, but you all also will realize that you should hold on to these moments, that this opportunity that you have here. So I think it's fantastic that TIFR does this Vidyan Vidushi program. I'm very happy to come and share my little bit of my interest with all of you here. I come from the Department of Physics at IIT Madras, and I work on quantum computing. And I just threw a little bit of Latin in the title because it was alliterative. I mean, Q and all that. But today, I'm sure everyone has. Why is this not? Oh, yeah. So. Quantum computing has been in the news, so I'm sure everyone has heard about it, right? I think the sort of, if I may use the word hype, started sometime around 2019 when Google sort of put out this paper. In this news item, it says leaked paper, but it was an actual journal paper published in the journal Science, where they claimed to have achieved something called quantum supremacy. This is, of course, a sort of unfortunate choice of word, I think, which today people talk about this as quantum advantage. People don't use the word supremacy anymore. But this sort of set off, triggered a lot of interest on quantum computing, which until then had been of interest to a few academics, maybe, and a few computer scientists, physicists, mathematicians. But this sort of then became, news. Right. So, and then, of course, IBM said they have a 400 qubit processor in 2022. And last year, Google was again in the news because they claimed to have done something with 105 qubit quantum chip and so on. And of course, other companies are not far behind. So there are now even much smaller players in the market. QEra, IQM. If Google and IBM are in the race, then Amazon can't be far behind. So there's Amazon's quantum chip and so on. But all of this one should take with this sort of statutory warning at the bottom, which was given by a Nobel laureate in physics from 2012, Serge Haroche. In fact, I think this was when he was visiting TIFR in 2012, if I'm not mistaken. He won the Nobel Prize in Physics for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems, this being the key. So this, in a sense, was what set off the whole field, the fact that one could do experiments where one could measure and manipulate individual quantum systems. So, in a sense, a pioneer of the field. But then he sort of puts out this warning, and this is almost 12 years ago, if not more, where he says quantum computing is trapped between hype and hope. And this is a very fine line that we are straddling today between hype and hope. So in this talk, I hope to sort of tell you a little bit about the hype and what the hope is also, right? Okay, so where are we today? So today we are in an era of what is called noisy intermediate scale quantum devices, right? And this is abbreviated into NISQ. Again, when you read the news, you will find this abbreviation bandied about a lot. So what does a quantum computer look like today? How many of you have seen this picture? Okay, yeah. So if one showed this picture, you would say quantum computer and not chandelier. Yeah, okay. So this is what a quantum computer of today looks like, right? Now, where is the computer in this? Chip that's inside. Very nice, yes. It's a little chip that sits deep inside here. So what's the rest of it for? Excellent. So you all know then. Okay, so then I can finish all my slides today then. Okay, so this is the chip that was in the news in 2019, 2020 from Google. This is called the bristlecone chip. So this is sitting deep inside here. This whole thing is sort of a dilution refrigerator with a lot of control electronics that is wired in order to be able to access and address these 72 qubits individually, right? And indeed, this is what you will find any company today that says it has a quantum computer. This is what it will look like. But the architecture of the chip itself could be somewhat different. This is a company called Rigetti that's based out of California, also, which has now maybe a 50 qubit processor. This was one of their older 16 qubit processors. This is what the IBM Q1 processor looked like, and so on. So the aim of this talk is to tell you a little bit about what is a qubit, okay? And why are we counting qubits? As in, why are we saying that I have, a company has 70 qubits, 100 qubits, 400 qubits? So what is this business of counting qubits? And if really this quantum computer is going to be sort of as big as the size of this room, then why should one sort of invest in building something like this, right? What is the advantage of going through all the pain of doing this, right? Okay, so a quick sort of intro to qubits. Yeah, so we all know about bits, right? This is just a binary random variable. If I were to abstract out what a bit is. So in a similar way, if I want to abstract out what a qubit is or a quantum bit is, you might have seen stuff like this. How many of you have seen this? Okay. So what is it? Is it just that I'm now saying 0, 1 with like this sort of line and sort of angle bracket here? What happens when I do this? So what happens is I'm moving from what was a binary field to now a linear vector space, right? So a qubit is something that is represented by a two-dimensional complex linear vector space. Okay, and I'm going to assume that you all know what that means, right? So it means that I identify a pair of basis vectors in the vector space in terms of which I can represent all other vectors in the space. So my qubit is essentially identified by a pair of such basis vectors, one of which I label 0 to correspond to the classical bit label 0, and the other I label 1 to correspond to the classical bit label 1. And then I form a vector space out of this, a complex linear vector space out of this, right? So now I don't just have two possible states for my qubit. I have many, many possible states because now I can make arbitrary complex linear combinations of this form. So I can I can also have a label psi, right, which is basically some A0 plus B1. So these in the physics language are called kets, right? So when you put this little sort of the way you represent vectors in a vector space, so these are called kets. So this is A ket 0 plus B ket 1. And A and B are complex numbers, but they cannot be arbitrary complex numbers. Because for me, a quantum bit is something that is also a physical object. It is a physical object which has to correspond to a valid quantum state of a system. Okay, and the laws of quantum mechanics tell me that these complex coefficients here cannot be arbitrary. They have to satisfy some constraint. In particular, they have to, in order for this to be a valid state, it has to be so-called normalized, which means that modulus a squared plus modulus b squared should be 1, right? So this is a sort of concise definition of what a quantum bit is. So I've said all of this. And of course, I can think about representing it as a column vector like this. I can do this matrix representation, and this is some representation that I have chosen, right? Okay. And so a general state would then look like this two-column vector with entries A and B, right? Now, this is the mathematical description, but what would be a physical description, right? So physically, a quantum bit, like I said, should correspond to a two-level quantum system, okay? Now, what does that mean? So I often like to introduce this with an example, which is something that we often encounter even in our day-to-day lives. This is basically the polarization states of light. I know a lot of you may have left physics after high school, so this is going to be a couple of slides of physics out here. But hopefully it's something that's not too complex, pun intended. Okay, so we all know about the photons, right? We all know that light is an electromagnetic wave, okay? Now, light is an electromagnetic wave. It is what is called a transverse electromagnetic wave. Yes, you all remember that? What does that mean?
Then its motion is perpendicular to its direction.
What is perpendicular to its direction?
The motion, the wave, the compression and refraction.
There's no compression and rarefaction in light. Yeah, that's for sound. Yeah.
Waves.
Okay, so what is oscillating? So something is oscillating, and it is oscillating perpendicular to the direction of motion. Yeah? Okay, what is oscillating? No. I heard this somewhere. Yes, exactly. Electric and magnetic field. So light is an excitation of the electromagnetic field, to be more precise, but it's basically oscillations of the electric and magnetic field vectors, right? And these oscillations are to be perpendicular to the direction of motion. That's what makes it a transverse wave, right? Now, if this is my direction of motion, I can think of different. So once I fix a certain direction in which the light is propagating, then there's a plane in which my electric and magnetic field vectors can oscillate, right? And the sort of precise direction in which they oscillate fixes for me what's called the polarization of light, right? Now, I can think about having vertically polarized light of this type. I can think about having horizontally polarized light. I can think about cross-polarized light this way and the other way as well, right? And if you think about this, this actually represents, so I can represent these states of light, these different polarization states of light, exactly using the mathematical apparatus that was in the previous slide, namely a two-dimensional complex linear vector space, okay? So this is one simple example of what a qubit can be. And in fact, this was one of the first realizations of a qubit way back in IBM in the late 80s, where people actually performed a quantum information processing task using simply polarization states of light, right? So it's a very precise analogy, and it's actually something that one can easily wrap one's head around, right? Okay, so the direction specifies the polarization. Recall that it's a transverse EM wave. So now I can sort of go back and assign this abstract qubit 0 and qubit 1 labels to specific things like vertically polarized light, horizontally polarized light, right? So this constitutes a physical realization of a qubit. And because of the fact that this can oscillate in a plane, and because of the fact that it also carries with it this complex phase, essentially the mathematical representation of this polarization degree of freedom boils down to a two-dimensional complex linear vector space. Okay, right. So let's look at this a little bit more in detail. Now, when I think about this polarization qubit, I already understand something just from my physical day-to-day experience, which is that, you know, we all use these, right? And you know that the principle that in which it works is that it's going to block certain polarization degrees of freedom, right? Certain directions of polarization. So in particular, If you've been, I don't know if in high school physics lab you do this, but definitely in undergrad physics lab you do this, where you would use what are called polarization filters, right? Which is essentially what your glasses contain, right? These Polaroid glasses contain. So if I have a horizontal polarization filter, then that does not let vertically polarized light through and vice versa. Now, this for me is a physical manifestation of a mathematical property of these vectors in the vector space, which is the fact that they are mutually orthogonal vectors, right? So I already kind of said that they are basis vectors. If they have to form a basis, then they have to be linearly independent. But then I also sort of can make them orthogonal without loss of generality. So these ket0 and ket1, the 0 and 1 states, which form the basic states of my qubit, are a pair of orthogonal states, right? Now, to again go back to the classical analogy, classically, we just have the bit value 0 and 1. Quantumly, we don't just have the 0 and the 1 state, as we just saw, but we have arbitrary combinations of these that can be formed. Now, what happens? So when I form such combinations, I actually lose this property of orthogonality. So in some sense, classically, this orthogonality is something that is underlying many of the information processing tasks that we do. But quantumly, if you want to mimic what the classical system is doing, then you have to come back to these kind of orthogonal states. And the fact that they're orthogonal is physically reflected or physically apparent when you use objects like filters, which essentially pick out a particular state and block everything else. This picking out of a particular state is something that technically I will call a projection. So what this is doing is it's projecting out to one of the polarization directions and therefore keeping the other polarization direction out. That's one way to understand what this is doing, right? So when I have a pair of orthogonal states or orthogonal vectors, I can construct such projectors, right? But if I now, so this is just a cartoon to say that if I now, instead of having a vertical or horizontal polarizer, if I now have a 45-degree polarizer or a 135-degree polarizer, then what happens if I now shine vertically polarized light on this? It's not going to block it fully, but it's going to block certain component of it, right? So now you actually see this idea of a projection at work. This is something that is projecting, let's say, along 45 degrees. And when I tilt it the other way around, it's going to project along 135 degrees. So now I have this cross-polarized projectors, which will allow a certain fraction of the vertical or the horizontally polarized light through. So if I go back to my qubit language, first of all, let's see how I can represent these states. So in our notation, this 45-degree polarized light can be represented as this kind of a linear combination. Remember, we said we can make linear combination. This should be apparent in that plane picture that I showed you. This is basically, cos pi by 4, right? Cos and sine pi by 4. And now this one comes with a phase, right? So it comes with a negative sign. So this is your 135-degree polarized, right? This is your. So these are also interesting states of my qubit. So I call them plus and minus. Okay. And now with just these 4 states, we can show things, ways in which a qubit behaves differently from a classical bit. Okay. Maybe I have that coming up later, but okay. So let me, so I have that coming up in a few slides, but let's go back a little bit. Okay. So now we just talked about 2 such combinations. Now, of course, I can make many more of these combinations. All right. So then how many possible states can my qubit access if I'm allowed to make arbitrary complex linear combinations like this? Infinite. Yeah. So there are infinitely many such states that I can make, right? So you already see how this contrasts to the classical bit, which can exist only in a pair of states. But now, how does anyone keep track of this, right? So you can now see that your state space has grown, right, from what it used to be in the classical case. But is there a simple way to keep track of this? It turns out that the answer is yes, because again, quantum mechanics imposes certain constraints. So let me just talk a little bit about a simple way to represent a qubit geometrically. So that's what's coming next. So this is, like I said, complex linear combination, but we need these states to be normalized. So these complex amplitudes have to square and sum to 1. And this, you can see, can actually be parameterized nicely with a pair of angles, right? So this is like a cosine and sine function, right? So if I represent the complex amplitude A with a cosine function, then the complex amplitude B should be a sine function. But this is only the amplitude, so I also need to take care to make sure that there's a phase, okay? But you could ask, why is there only one phase? What happened to a phase out here? Once again, quantum mechanics tells you that if I were to put a phase out here, I can always sort of pull out what's called a global phase, and what remains is only this relative phase between the ket 0 and the ket 1. Okay, and this global phase is not an observable in quantum mechanics. It is not. So physically, I cannot distinguish between, let's say, ket 0 and e to the I pi by 2 times ket 0. Okay, physically they correspond to the same state of a physical system. So also for qubits, they correspond to the same state. So the overall phase doesn't matter. What matters crucially, however, is the relative phase, which, as we saw, can really change the way the state looks like from, say, horizontal, vertical to cross-polarized line. But now I don't just have these 4 states, I have this infinity of states. So I have now parameters which describe for me 2 real parameters which describe for me the state of a qubit. So you can see we have gone from 2 complex numbers which describe the state of a qubit, which should be 4 real numbers actually, but kind of reduces down to 2 real numbers from physical constraints. One angle, so I've made this a half angle, basically because, well, when I think of 2 angles like this, what can I think of? I can think of a sphere, right? And I can think of essentially latitude and longitude on a sphere, right? And this is a sphere of unit radius, right? Because all of these amplitude squares is 1. So that's exactly what we have. So a quantum bit can be represented via a unit sphere in 3 real dimensions, okay? So you can parameterize it any which way, but let's say I choose to put ket 0 at the top, I choose to put, okay, so maybe this is a bit of an exercise for you. If this is ket 0, and so I don't know if I've marked the general state, not marked the general state here. Okay, so for me, sorry, yeah, so I showed you 2 angles. So there's one angle which, so let's say that this is a z-axis, okay, and this could be x and y. So the angle theta is basically the angle with respect to the z-axis, and then the angle phi would be when I drop a perpendicular from any point on the surface of the sphere to the xy plane, and then I take this angle out here. So one of them is a polar angle, one of them is azimuthal angle, and using that you can parameterize all the states that a qubit is allowed to be. There's a sort of one-to-one correspondence between points on the surface of the sphere and the state of a qubit. I've just identified a few specific states here. So this is the 0 and 1. This is the plus and minus, right, which we saw corresponded physically to 45 and 135 degree polarized light. Now, instead of just having this cos pi by 4, I can now have cos pi by 4 with a complex phase instead of a real phase. So this comes with a plus I and minus I, and you can see that they will correspond to the points where the y-axis, the diameter which lies along the y-axis intersects with the sphere, and so on and so forth. So you can sort of identify, and maybe it's not so hard to convince yourself that any diameter that you draw for this sphere, where it intersects, the points where it's going to intersect the surface here are going to correspond to a pair of such orthogonal states, and that constitutes an orthonormal basis in which I can describe my qubit, right? And 0 and 1 are just some arbitrary reference labels that we use, okay? So why is all of this now interesting? Of course, so yeah, when I give this talk to high school students, sometimes I tell them, so you see the classical bit can just access the north pole and the south pole of the sphere, but now your quantum bit can access the entire surface of the sphere, right? So that's what is sort of mind-boggling, that now suddenly your state space that your unit of computation can access is now expanded tremendously, right? But can one really access all these states in a physical sense? In a sense, can I really store information in all of these states and retrieve information. So now the question becomes, how do you store and retrieve information in these quantum states, right? So there are now some do's and don'ts that come into play, okay? So the first thing we notice is, of course, this aspect of non-orthogonality, right? The fact that you now have non-orthogonal states in which your qubit can exist. So what do I mean by that? So if I go back to, here. So we saw that this plus and minus, while plus and minus themselves are mutually orthogonal, they are not orthogonal with respect to 0 or 1. And this was the reason why when you shone vertically or horizontally polarized light on a cross-polarized filter, you're still going to allow some light through, you're not going to block it completely, right? So you have these non-orthogonal states, and now it turns out that you encounter a problem with these, just as how it was an advantage in the sense that you now have an expanded state space. At the same time, you now have a problem because non-orthogonal states cannot be perfectly distinguished. And a very simple naive example using the polarizers and filters tells you that already. The way I would distinguish, for example, whether the light that was coming to me is vertically or horizontally polarized is by putting one of these filters in the path of the light and then seeing whether that allows the light to pass through or not. But now, if we play a game where you tell me that the light is either going to be vertically polarized or 45-degree polarized, okay? Now I have to design a filter which is going to detect this. Is that possible? You understand the problem that like I said, we play a game where you prepare light which is either vertically polarized or 45-degree polarized, which means you prepare states either in ket 0 or in this plus state, which is now a combination of plus of 0 and 1. Can one construct a filter which is going to detect which of these possibilities happened, right? And the answer is no, because if I were to use a horizontal or vertical filter, then it's going to allow both of them with some probability, right? And in the same way, if I were to construct a 135-degree filter, it's also going to allow both of these lights to pass through with a certain probability. And if one had 45-degree polarized light and one put a vertical filter there, how much light do I expect to see in terms of amplitude? Roughly half, right? That's what this 1/√2 tells you, yeah? So what I'm now trying to point out is that these complex amplitudes are not just arbitrary things, they're actually representative of probabilities, right? And this is something that one might have guessed just from the fact that these mod A squared plus mod B squared was coming to 1 is reminiscent of a probability distribution. So these complex amplitudes that are sitting in front of these qubit states are actually represent a probability distribution, right? And now, whatever I said in English words is the sort of more precise way of saying it is that one cannot design a quantum measurement which can perfectly distinguish between the ket 0 and the ket plus, between the 0 state and the plus. Okay? So this is what I was trying to say. A quantum measurement is like a projection. And with these filters, I was trying to give this analogy that what these filters are doing is essentially some kind of projection. And then you can sort of play this game with polarizers and filters and see that when you try to measure this state, which is a 45-degree polarized light, in the vertical horizontal basis, then you're going to actually get outcomes, both outcomes with probability half, right? Because you're now projecting the 45-degree polarized light onto the vertical and the horizontal axis. So, of course, equally likely that it's going to get projected onto one or the other, right? And vice versa, if I were to measure the vertically polarized light using the 45, 135-degree filters, again, both outcomes are equally likely. And so it is impossible for me to construct a quantum measurement which is going to distinguish between these states. So now you see that although you have this entire sort of sphere full of states which one can access, when one performs a measurement, which is how one finally interacts with the quantum system, which is how you finally read out information, then you can only read out as much information as you can with a measurement onto an orthonormal basis. Okay? So this is sort of the challenge in quantum information processing, that while you now have many more states in which you can encode information, with which you can do information processing, but finally when you read out, you're constrained to measure in these orthonormal bases, right? And these orthonormal bases come with some interesting properties. So like I said, you can construct many orthonormal bases. You can construct many quantum measurements for this qubit. But when I pick bases like these, 0, 1, and 45, 135, then it turns out that they correspond to what are called complementary properties. And this is something, again, that you must have heard in school, the famous uncertainty principle, right? Of course, in school, one was taught that it is not possible to simultaneously determine the position and the speed or the momentum of a quantum object, right? But you don't need to go into such fancy things. So position, momentum, if you think about it, are actually also correct. You can also sort of represent them in this linear algebra language, complex vector spaces and all, except they are now infinite dimensional vector spaces. But even with very finite dimensional vector spaces, that just two-dimensional vector spaces, you see this uncertainty principle in play, namely that you cannot simultaneously obtain precise information in both the 0, 1 and the plus minus bases, right? And this is what one kind of saw with all this example of these polarizers and these filters. So such properties are called complementary properties. And this is, again, sort of a fundamental, it's just a mathematical, consequence of being in this complex linear vector space, and one can essentially prove this uncertainty principle just using Cauchy-Schwarz inequality on this vector space, right? So it's a fundamental mathematical property of the fact, a consequence of the fact that these states live in these kind of complex linear vector spaces. Okay, so any questions so far? All right. Okay, so now what can we do with these quantum bits? So I want to show you a simple quantum algorithm that can be run. Again, using sort of elementary quantum gates and so on, right? So yeah, this is a kind of interesting thought that one can sort of ponder about. What computers can and cannot do is determined by the laws of physics alone and not by pure mathematics. So David Deutsch was a physicist who came up with one of the earliest examples of a quantum algorithm, the so-called Deutsch algorithm, and I'd like to give you a flavor of that. But before that, I've only told you about the landscape of the qubit, what it looks like, and the fact that now you have to deal with non-orthogonalities and all that. But how do you compute? So you need gates. What are gates? So here, I'm going to think about gates as mathematical transformations of these quantum states, right? Like mathematical and physical. But so what kind of mathematical objects would gates be? Matrices, yes. So here's the classical NOT gate, and then here's the quantum NOT gate. So again, you see the difference out here. So now you not only transform the 0 to the 1 and the 1 to the 0, but you now have to transform all such complex linear combinations corresponding, right? So of course, these complex linear combinations are what we call superpositions. So I've tried hard not to use the word, but then, so these are superpositions, and a quantum gate must therefore transform these kind of two-column vectors, if you will, complex vectors, right, from one to the other. In this particular case, it's this kind of a transformation. So you can figure out that this is the transformation matrix, and this is what we call a quantum X gate. Okay. So similarly, you can see that since these are now two-dimensional vectors, gates are essentially going to be 2 cross 2 matrices, right? But are all matrices allowed? Can I construct any arbitrary 2 cross 2 matrix and call it a quantum gate? No, because again, this constraint has to be satisfied. Now, since I've mentioned that these are probabilities, this is basically a constraint that talks about conservation of probabilities. Okay, so this says, for example, that if I measure my qubit in the 0, 1 basis, I better get numbers which add up to 1, right? I better get statistics or probabilities which add up to 1. So in order to preserve this, which is essentially preserving norm, I need to have norm-preserving transformations. Norm-preserving transformations are essentially unitary matrices. So quantum gates are essentially unitary matrices, right? So all single qubit gates, which means now I'm going to soon talk about multi-qubits and multiple qubits and so on. Single qubit gates are essentially 2x2 unitary matrices, right? Okay. What about multi-qubit gates? Now, classically, you think about gates as at least the fundamental building blocks out here. All of these you're all familiar with. They take two inputs and give you one output, right? Now, quantumly, you find that if you want to do a deterministic transformation of the state, okay, then it has to be a unitary transformation. But by definition, unitary matrices satisfy a nice property, which is what? Okay, are people familiar with unitary matrices? I just went off and, yeah, what are unitary matrices? Sorry? More clearly. Yeah. A
Sorry, is it
determinant is one, okay.
So column dot column.
Okay, but all of those properties come from a definition, or at least that's the way I like to think about it, which has something to do with the inverse, as you mentioned, right? Which is what?
A transpose A.
Okay, so it's not just the transpose anymore because we are now dealing with complex matrices. So you have to think about the transpose with the complex conjugate. So that's what we call an adjoint operation. So A adjoint has to be identical. Or in other words, the inverse is the same as the adjoint, which then tells me that all these gates, if you think about it, come with an inverse. Yeah, which means they're all reversible, which is again very unlike what happens in a classical computing scenario, right? So all quantum gates are unitary operations and therefore by definition reversible because the inverse is simply the adjoint of the matrix itself, okay? So when I think about a 2-qubit gate, for example, it takes in two inputs, it has two input registers and two output registers. So the sort of most canonical example and the most important example of a 2-qubit gate is something called a controlled NOT gate, okay? You're familiar with the standard NOT gate, but this now says it flips the state of one of the registers depending on the control state of the controlled register. So there are two registers, one of which is a control and the other is a target, and the target is flipped if and only if the control is set to 1. And this turns out to be a very useful gate in quantum computation. So this is how we represent the gate. So this is how we represent, so this you can think of as a very elementary quantum circuit. You read sort of time flows left to right. These are my two input registers. These are the two output registers. And what's happening here is that it actually, this state depends not just on the Y register, but also depends on the X register. Okay. Now, there is an interesting quantum mechanical feature that's hidden in this circuit. Of course, I can write down a matrix representation for this and all of that. But you see, what's happening is now the state of the second register after the action of this gate depends not just on this second register, but also on the first register. So this contains information about both these qubits. Okay, and this is one of the ways of realizing an important quantum feature called entanglement. Because now, with certain kinds of initial states, you can actually get states out here which are no longer representable as simply a state of the control and a state of the target. You will have to represent them via a joint state of the 2-qubit system. So this is an elementary entangling gate and is at the heart of many quantum information processing tasks, whether it's algorithms or error correction and so on and so on. Okay. All right. So this is how the matrix would look like. And well, so if I want to construct a meaningful model of computation from this, I need to ask about universality, right? I said any unitary matrix is a quantum gate. That's all well and good. But can I realize this using a basic set of gates? Can I implement any quantum circuit? If I have the ability to implement a few basic gates, can I go ahead and implement any arbitrary quantum operation, any arbitrary circuit, right? That's what universality is. And there's a very nice result which says that any multi-qubit logic gate operation can be implemented simply using CNOTs and single qubit gates, and this can be refined further into an elementary set of single qubit gates and so on. We'll not get into all of that, but just want to say that there are some very nice universal gates. So today when Google says they built a quantum processor, they have demonstrated the ability to implement this basic set of universal quantum gates. This includes, for example, a control NOT gate. It includes an X gate. It includes something called an H gate, which we will see, and a couple of more gates. And this is enough for us to guarantee universality. Okay. All right. So now what can you do with superposition? So now that I've showed you quantum gates, can I show you a simple quantum algorithm? So the basic quantum algorithm which I want to show you is the so-called Deutsch algorithm, which is a very nice demonstration of quantum parallelism, right? So what is parallelism? So the idea is sort of, again, very loosely speaking, that instead of the classical case where if I now have a single bit Boolean function and I want to evaluate this function for both 0 and 1, the way to do it is to input 0 first, get the output, input 1, and then get the output. But now, because I'm allowed to prepare states in superposition via complex linear combinations, then it kind of follows that I am now able to implement functions in a way simultaneously on both the qubit state 0 and the qubit state 1. Okay, so this sort of is the idea of quantum parallelism, and here's a simple way to do this. So this is the function, right? Now you can think of this function as some kind of oracle. If you're familiar with sort of oracle model of computing, this could be an oracle. So this is, for example, a classical oracle, and what I'm presenting here is a quantum version of the same oracle, right? And now this quantum version is more powerful, quote unquote, than this classical one because it is going to evaluate both function values at the same time or in one shot. When I say at the same time, it just means that it is one shot, right? So what does this do? So this U is to indicate that this is a unitary transformation mathematically. It takes two registers, X and Y. And remember this controlled operation which I told you about? This is now a slightly tweaked version of that controlled operation where the second register is now going to take the value Y XOR F of X. Okay. And now this first register, I don't just input 0 or 1, I query, so to speak, this quantum oracle via a superposition. Okay. And then what happens at the output is I end up with a state like this. Okay. So if I query with 0 plus 1 over root 2, I end up with a state. And this is an example of what I was telling you, which is quantum entanglement, right? So this final state of these two qubits, I cannot represent simply as a state here, tensor product a state here. Rather, it is actually a combination of two such product states. So if the first qubit was in 0, then the second qubit would give me the value f of 0. If the first qubit was 1, then the second qubit would give me the value f of 1. So using this quantum oracle, in a way, I'm simultaneously able to access both f of 0 and f of 1, or rather able to access them both in a single shot. Okay. Right. So now if I want to evaluate f of 0 or f of 1, what I need to do is measure the first register. And by measuring the first register, if the first register is in 0, I get f of 0. And if the first register is 1, the second register is f of 1. Now, you can stop here, me here and say, but you're not really accessing f of 0 and f of 1 simultaneously. Because you are doing a measurement, right? So the way I'm able to access these values is by measuring the first qubit. And when I measure the first qubit, it is not in my hands as to whether the first qubit is going to collapse to a 0 or a 1, right? And depending on whichever outcome it is, I'm only able to access that value of the function. So is this really useful? Now, this is where the design of a quantum algorithm comes into play, right? You need to now design a way to leverage the fact that your system somewhere knows both these values, okay? So can you now leverage that knowledge in a useful sense? And that is what the Deutsch algorithm does. Okay, it was the first example of a quantum speed up that was demonstrated. And it was done for this toy problem, which is basically this. You have two parties, one of whom selects a number which is basically an n bit string, right? So from 0 to 2 to the n minus 1, you have all possible n bit strings. So A selects one of these n bit strings, and B has to evaluate a Boolean function and send the outcome, which is 0 or 1, to A. Okay, and A's goal is to determine whether this function is, so you're given a promise in this problem. So a promise is basically something which tells you that there are some constraints that this function is satisfying. So this function is either constant or balanced. Constant means it is the same for all n bit strings. Balanced means it is 0 for half the values and 1 for the other half. So given this promise, the goal of this game for A is to determine whether this function is constant or balanced, and each time A sends a string to B, she loses a point. Okay, so what is the least number of queries in which A can actually determine whether this function is constant or balanced? So this model, which even in the previous slide I'm talking about, is what's called this Oracle model of computing. You're all familiar with this? Query complexity. So where does this word Oracle come from? Greek mythology. So who was the Oracle? Yeah, so the point I want to make is a female goddess who was the Oracle. So you could ask her anything and she would give you answers, but now you have a currency to pay for every time you ask her a question. Okay, so what is the least number of queries in which you can succeed? So this is query complexity. And so what is the classical query complexity for this?
Big O of n.
What is big O of n?
Like you will have to make at max n by 2 plus 1 queries to the top. Wait, 2 to the power n by 2 to the power n minus 1 plus 1.
Yeah, so this is exponential even. This is not n by 2. This is 2 to the n by 2. Yeah, plus 1. Yeah, okay. So I hope everyone is on the same page with that. So this has exponential query complexity. Okay, so yeah, so that's what I say here. Now, it turns out that quantumly you can do this with just one query. Okay, so it's constant. It's not even linear, it's constant. Okay, so how do you do that? Well, instead of querying each time with one of these n-bit strings, A is going to prepare a massive superposition of all these possible 2 to the n possible strings, right? And just sends this as one query to B, okay? And B just has this quantum oracle, right? This kind of this unitary matrix that I had shown in one of the slides. And so simultaneously, B evaluates all of these function values. But now A does something more than just send this one query. And you can say maybe now this is cheating. You're allowing the quantum oracle, the quantum model to do a bit more, but then the quantum model can do more. It can do what is called interference. Okay, so it can interfere the different states in the superposition. And based on this interference, whether this is constructive or destructive, A is then able to determine whether this function is constant or balanced. So we'll see an example of this with just the n is equal to 1, which is the single, it's a single bit Boolean function now, right? So there are only two possible, so now it's not even a promise, right? The function is either constant or balanced. This is a single bit Boolean function. And this is the same circuit that I showed you, except that I have now added something here, okay, namely this H gate. Okay, so this is a quantum Hadamard gate. In fact, this is the gate which first of all rotates the zero state into this state. Okay, remember this block sphere. Now the zero state was the north pole. Any transformation I can think of essentially as a rotation on the sphere, right? So I'm now rotating the zero state down to the XY plane to make this plus state, okay? And this is in fact the quantum gate that will do that for you. So essentially you have a Hadamard gate here and a Hadamard gate at the end, okay? And what this Hadamard gate is doing is essentially this interference where, remember here you had a state which was entangled, and from that you could not really obtain the values f of 0 and f of 1. Now you're still not obtaining the values f of 0 or f of 1 here, but you're able to in a single shot compare whether f of 0 is the same or different from f of 1, which was the stated task. The task was not for you to determine what is f of 0 or f of 1, but to find out whether f of 0 and f of 1 were the same or different. So in some sense, you're accessing a global property of the system and not a local property. And this is something that quantum circuits are able to do exponentially faster than classical circuits. So this is the sort of overall summary that I told you. The details are here. You can work them out if you wish. But basically, what this H gate will do is this state here at the end of this side 2, it will show up as 2 different states, okay, depending on whether f of 0 is the same as f of 1 or different from f of 1, okay? And that is what this algorithm does. It tells for you whether this function, all the bit strings evaluate to the same thing or whether half of them evaluate one value and the other doesn't, right? And the way you've kind of cheated the system is you have prepared, note that you have prepared both registers in superposition here. So this is in the plus state, this is in the kind of diametrically opposite state on the sphere, what we call the minus state. And by preparing and querying in superposition, you have managed to access this global property of the function via a single query, okay? All right, so yeah, so for the single bit case, this is twice as faster. For the n bit case, it is exponentially faster. Okay, so this was just a flavor of how a quantum algorithm would work and why it would offer advantage over the classical setting. Okay, but this was just a toy problem. What is it useful for? Sounds like a parlor trick, but there are indeed practical problems that can be solved much faster on a quantum computer. So there is the search problem, right? Searching over an unsorted database, and you all probably heard the Grover algorithm. Note that here the speed up is not exponential but quadratic. Okay, and this is another lesson that not every task may admit an exponential quantum advantage. Okay, so in the case of search, this is in fact known to be optimal, which means that you cannot have a quantum algorithm that searches faster than Grover algorithm. Okay, so you do not have exponential speed up in this case, but of course with factoring you do have exponential speed up. So what requires of the order of 2 to the n now requires only n squared log n for factoring an n bit number, and this was very recently improved actually by Oded gave to n to the 1.5, and there are now more tasks added to the list. So this was all done in the 90s, and then we had kind of a period of drought for about 20 years when there were no new quantum algorithms in the picture, and people began to question whether, you know, a search and factoring sort of the only examples that you have for, quantum speed up. But more recently in 2008, it was shown that you could solve, you could basically do matrix inversion exponentially faster on a quantum computer. And today we have a few more such algorithms demonstrating different kinds of speed up, right? And so this is how quantum computing basically changes the factoring, the complexity landscape. So this is the sort of classical picture that one is used to. But now you have here something called BQP. So all the algorithms that I have described fall into this category of bounded error quantum polynomial time. And it's a kind of funny picture because it's taken from Scott Adams's blog, because we really don't know where these boundaries are. We really do not know if this stretches all the way to hit the NP-complete problems. So plenty of sort of work to be done out here and a lot of interesting questions that one can ask here. Okay. All right. Questions? Okay, so maybe I will just skip to the very last part of my talk because I'm hitting the 1 hour mark. So I will not tell you about no cloning and entanglement, but I'll tell you a little bit about my own interest, which is here. So in theory, quantum computing works very well. But then the question that I asked at the very beginning, why are we counting qubits? Why are we saying that? So first of all, do we have a fully functioning quantum computer yet? Have we managed to factor, I don't know, even 100-bit RSA numbers? Not really, right? So why is that, right? Because, well, as the great physicist Asher Perez liked to say, quantum phenomena do not occur in a Hilbert space, they occur in a lab, right? So what does one really need in order to build a quantum computer? Okay, so you need a scalable system with well-defined qubits Now, I gave you this example of the polarization states of light, but as you can imagine, these are somewhat fragile states, right? How do you, so even as this light comes from, of course, this is unpolarized, right? But even if you were to prepare a highly polarized beam of light, you can imagine that very soon this polarization is going to deviate from the exact sort of state in which I prepared it in. It's what this process is what we call depolarization, right? So as this beam of light traverses through an optic fiber, or as it is beamed, let's say, from space or whatever, it's going to lose this fidelity of polarization, right? So this is a very fragile implementation of a qubit, right? And this is the reason why, although it was one of the earliest implementations of a qubit, it is not something that today we do not see quantum computers being built out of polarization qubits, right? We see them being built out of these chips which have what kind of qubits? Does anyone know? There are some photonics-based qubits, yes, but most of the architectures that I showed you are all superconducting qubits. Okay, so you are essentially, and like I said, they are huge refrigerators. I think I mentioned that, and they are huge refrigerators because you're essentially cooling these chips down to millikelvin temperatures. Okay, in order to make sure that the superpositions that you prepare them in are maintained with high fidelity for a sufficient duration of time in which I can do a meaningful computation. Okay, so what you need is a scalable system with well-defined qubits. You need to be able to initialize to a simple fiducial state like your ket zero, whatever is your the zero state. You need long decoherence times, right? And this decoherence is what I was telling you about, that the superposition that you prepare may not survive with high enough fidelity for a long enough time, right? And this is sort of called loss of coherence in physics terms, or decoherence, right? And of course, you need to be able to perform a universal set of gates. And last but not the least, you need to be able to read out information from these qubits, which means you need to be able to perform high fidelity single qubit measurements. Okay. So these are often called the DiVincenzo criteria, and any physical system which admits these criteria is considered to be a worthy enough candidate for a quantum bit and eventually to build a quantum computer. But today, the sort of main issue that we are grappling with in going from a handful of qubits, chips with a handful of qubits, to a truly universal quantum computer, the main issue that one is dealing with is this decoherence, right? Which is basically irretrievable loss of information. Now, why does this happen? Why is it that this polarization state, as it traverses through a beam, why does it sort of deviate from the state in which I prepared it in? Because this beam of light is going to interact with the fiber optic cable, and when this interaction, through this interaction, it is going to dissipate. It is going to dissipate energy in physical terms. In information theoretic terms, it is going to lose information. Okay? And because this information loss is not happening in a deterministic controlled fashion, it means that it is no longer this sort of very nice unitary transformation that one was talking about. So in mathematical terms, this is now an irreversible transformation. Okay? So now this is what is called noise in quantum systems. And then one needs to now invoke tools from error correction to address this. Okay? So can I go on for 5 more minutes? Yes, sorry. Okay, so this is just to tell you how qubits have been scaling. It's a slightly older picture. Today, of course, we've gone, most of these companies or qubit makers have gone beyond 100 qubits. Yeah, so this was to say that, okay, there's some kind of sort of linear Moore's law one can have when it comes to these specific kind of qubits that I spoke about, which is the superconducting qubits. And yeah, so we are somewhere here, right? So this coherence time, which is on the y-axis, tells you how long does a given qubit last in the superposition state that I prepared it in. Okay, it's very loosely speaking. Of course, I have to use very precise measures like fidelity or distance to calculate exactly how close I am to the state that I wanted it to be. But you see, we are somewhere in the regime of 1,000 microseconds. So we are roughly at about milliseconds, and maybe a few tens of milliseconds today, or hundreds of milliseconds today, right? But it turns out that this is obviously not long enough for me to be able to leverage the advantage of quantum computing, right? Because the advantage really lies not in doing a toy problem like the Deutsch problem, but in doing something like factoring. And in factoring not 15 into 3 and 5, but into factoring to 200-bit RSA numbers, right? So the kind of scale that it requires, right, and the depth, the circuit depth that it requires, while it scales very favorably in theory with classical computers, in practice, the qubits are simply not alive enough, long enough for us to be able to perform something like factoring on them. Okay, and so the main task today is to see if we can somehow increase this so-called coherence time of a qubit and make it more long-lasting. Now, to do it at the physical level is, of course, an engineering challenge, and people work on that. But one can sort of try to do this at a logical level, and that is what error correction does. Okay, so this is the sort of article which I encourage you to read. It's a very nice sort of summary of where we are today. I mean, it's 7 years ago, a little bit dated, but still not too dated. And it talks about the challenges, which is basically noise, right? And it's not just noise in the qubits, but also noise in the quantum gates. And if one is able to use quantum error correction and effectively suppress this noise, then we can actually unlock the potential of quantum computing. So why does noise happen in quantum systems, and how is it different from, let's say, noise in classical systems? Because we have been dealing with noise in classical systems for 100 years now, maybe, right? So can we simply use those techniques to address the same issue with these qubits, right? Now, like I said, these qubits live in this complex linear vector space. The qubits are not isolated objects, right? So if I prepare a superconducting qubit, which is basically a physical object called a Josephson junction, essentially, then it doesn't live in isolation, right? It is surrounded by the material in which you etch it on, and so on and so forth. And all of that becomes part of what is called its environment. And physical systems naturally will interact with this environment. And this environment is typically a system, another quantum system, with many, many more degrees of freedom. So it is not possible for an experimenter to really control this environment. What is possible for you is to control your qubit, right? So this interaction between qubit and environment, now I can think of them together as forming a closed system. Maybe they sit deep inside this dilution refrigerator, so they're cut off from the rest of the environment. So together, maybe they get transformed via these unitary transformations in a deterministic way. But as such, individually, my qubits do not transform unitarily, okay? And this leads to a kind of very different mathematical structure to the transformation. So I kind of illustrate this with a simple example of a quantum bit flip channel, for example. This is something that you may all be familiar with in the classical case. You're familiar with a bit flip noise in the classical case, right? Where your 0 can get flipped to 1. This is not a NOT gate, right? It's a probabilistic flip, right? So it flips to 1 with probability p, remains 0 with probability 1 minus p. So this is what you call a binary symmetric channel. You can make a quantum analog of this, and that's what I've done by putting these skets. But it's not as simple as that. If I initially started out in the 0 state, which is a north pole, I let my qubit be for some time, right? And suppose this bit flip noise, the environment is such that it causes the bit to flip in this probabilistic fashion, then after a certain amount of time, what state do I have? With probability p, I could have flipped to 1, and with probability 1 minus p, I could have remained in 0. How do I represent such a state of a qubit? It is no longer a superposition of 0 and 1. It is no longer coherent, but rather a statistical mixture of 0 and 1. It's an incoherent mixture of 0 and 1. So essentially, I've transformed from what was a pure state to a mixed state. Okay, and this is why this transformation becomes irreversible. Okay, and there is loss of information in entropic terms that you can associate in this transformation from a pure stage to a mixed stage. Okay, so this is just a simple. I'm not going into the mechanics of how would you represent a mixed state and so on and so forth. But it's no longer a superposition. All right. So, and of course, this probability with which it flips one can sort of relate it to time, and that is where this decoherence time comes into play, right? So I can sort of physically solve for this model and get a probability function, probability of bit flip as a function of time, and most models will give you something like this kind of exponential growth of this probability of bit flip with time, right? And so the time constant in this exponent is what is called the decoherence time. All right, so now how does one deal with this kind of noise? Classically, you would say, well, now instead of storing a 0, store 3 zeros. You would do what is called a repetition code, right? This is how you would deal with bit flip noise classically. So can one do this in the quantum case? Now, remember that in the quantum case, I'm not just storing zeros and ones, or I'm not just using zeros and ones in my computation. The whole point of quantum computation is to be able to prepare superposition states like this and use them to compute. Okay? So can I now do this, which is for every such state that I have, I now prepare 3 copies of this state. Now, this is forbidden by something called the no cloning theorem. One of the slides that I skipped, I wish I can show you in the end. But quantumly, so this is a fundamental classical information processing task which cannot be done in the quantum case. You cannot copy arbitrary quantum states. You cannot design a unitary quantum cloner, which is like a universal Xerox machine. You put in anything, and then on this blank piece of paper, you get the information that was there in the paper, right? This is not possible. And again, this goes back to the fact that you have non-orthogonal states, okay? So now, instead, what you need to do is you need to find a way out of it using, again, a quantum mechanical property, which is entanglement. So now note what this state here looks like. So I have now made this superposition A0 plus B1 into A000 plus B111. This state is a state of 3 qubits, which I cannot factor or write down in this fashion as the state of the first qubit, the state of the second qubit, and the state of the third. I cannot break it down into the state of individual qubits. So this is an entangled 3 qubit state, and the information actually resides in this entangled state, right? So you have introduced redundancy by increasing the dimension of the space. You've gone from 1 to 3 qubits, but also by introducing entanglement. And this turns out to be crucial for quantum error correcting codes. So this is the simplest quantum error correcting code. It's a 3 qubit repetition code. And this is a simple quantum circuit which can prepare this kind of a state. It simply uses 2 of these control NOT gates, which I told you about. And so you now have logical qubits from physical qubits. And instead of the physical 0 and 1, you now have a logical 0 and 1, which is now simply this 3 zeros and 3 ones. So in a way, it is analogous to your classical repetition code, but in many ways it is not, because it is now an entangled state of 3 qubits. There are some challenges when it comes to decoding and so on. I'll not dwell on that, but maybe just show you how one overcomes all of this. So we now have a very nice theory of quantum error correction that has been developed. But until very recently, this was only in the theoretical domain. So what happened very recently with Google, and I'm going to skip some of this, is this, right? So all the excitement last year from Google was not that they had demonstrated a new quantum algorithm or anything like that. It is simply that they had demonstrated a quantum error correcting code for the first time in a way which was beyond break-even. Okay, and what do I mean by beyond break-even? So this is sort of the physical architecture of Google's Willow chip. Okay, you notice that there are regions shaded in different colors. Okay, and there are qubits sitting here, right? It's like a lattice of qubits, right? And then you can sort of draw these plaquettes on the lattice, which represent certain measurements that you have to do for error correction. But now, not all of these dots here are data qubits. Some of them are extra ancillary qubits, which you use in order to detect for errors. Okay, extract what is called error syndrome. So Google has built this nice architecture of data qubits interspersed with syndrome qubits or ancillary qubits in order to implement a kind of error correcting code called a surface code. Okay. Now, when I put in this array of qubits all together, I have noise not just on one qubit. So let's say this array, so Willow had 100 qubits, right? The Willow chip had 100 qubits. So now I have noise on 100 qubits. And I don't just have individual noise on these qubits, I could even have correlated noise and so on and so forth. So what guarantees for me that if I put together this array of 100 qubits and prepare this kind of repetition code, encoded state that I showed you, what guarantees for me that the noise also doesn't scale up as I add more and more qubits? So that is where the error threshold comes into play. Okay, so this is the sort of physical noise threshold. And what Google showed is they implemented this error correcting code whose threshold exactly they were able to achieve. So they were able to achieve for the individual qubits a physical error rate which was below the threshold that was needed for error correction to work. Okay. But of course, it needed 100 physical qubits in order to implement a single logical qubit. So what Google showed is essentially a single logical qubit using 100 qubits, which are laid out like this array on a chip. Okay, so let me stop here. And of course, the challenges going forward are very clear, right? How does one make this scalable, right? So if you're talking about 100 physical qubits per logical qubit, how scalable is this? And how do you now make logical gates out of this? Are there more efficient quantum error correcting codes that we can build? That's one of the areas that my group works on. Are there better physical qubits that we can build? This is an area that a lot of groups work on, including, let's say, Professor Vijay's group in the physics department here. But essentially, this is sort of the holy grail now, right? Can we be somewhere here in this region? So you have the error rate, you have the number of qubits. So far, we've sort of been stuck here around 100 to even, IBM even brought out 1,000 qubit chips, but they were super noisy. So you were really sort of down below here in terms of the error rates. So can we actually sort of cross this and sort of be somewhere here where you can both do error correction also and start doing useful quantum computation? Okay, so let me stop here. Thank you.
We have that questions. Doesn't necessarily need to be technical also.
Are there constraints, like physical constraints about what categories you can apply?
What sort of unitaries?
In the sense that you would also want some sort of proximity between different qubits or something.
Yeah. So, okay, so what you need for universal quantum computing is only one 2-qubit gate. Okay, so the example I showed you was a C0, which actually needs 2 qubits to be proximate, right? And this is indeed one of the challenges. So if you look at IBM's chips, for example, the qubits are sometimes arranged in a hexagonal kind of array. And then if I want to implement a control knot between qubit 1 and 3, they're actually, I'll have to do what is called a swap gate, which is another 2-qubit gate, move the qubit, move the state. So the swap gate literally swaps the states of the 2 qubits, do a swap gate, then do a control knot, and then go back. So now this is, of course, inefficient. But interestingly, there are these cold atom-based architectures or neutral atom-based architectures. So there's a company called QERA. I think I showed that in my second slide in the list of companies, where those qubits can actually be moved. So these are arrays of neutral atoms, which are essentially function same like 2-level systems. But now, unlike superconducting qubits and so on, which are etched on a chip, you cannot move them, these are trapped via lasers. So by sort of changing your laser arrays, you can actually move these neutral atom qubits around. And that seems to be one promising architecture where you can now literally get all-to-all connection, but with some, so there the sort of trade-off is time, because it takes time to move these qubits around. So now, are you really gaining, this whole exponential speed up and so on? So that's the trade-off there. Yeah.
So other than factoring and like some very specific questions, if, let's say we did build a quantum computer and let's say even work at good temperatures. So what would like someone use it for? Like, can we extend these factoring problems to something like that is more useful in a commercial basis or like a regular day-to-day basis?
Yeah, that's a very nice question. I was hoping someone would ask that question. So beyond breaking passwords, what are quantum computers really useful for? A colleague of mine at IIT Madras likes to ask me this question all the time. Okay, so first of all, any problem in P can be solved using this. Okay, so we leave that aside. But the interesting thing with quantum computers and how they were envisioned to begin with by physicists like Richard Feynman is that quantum computers can act as excellent quantum simulators. Okay, which means that if I have a physical Hamiltonian or a physical model of multiple qubits, I can okay, so I'm trying to say this in a way that so let's say that you need to solve an optimization problem, right, which is all over the place. Now it turns out that you can map these optimization problems to certain physical models called Ising models. Okay, and there's a physical Hamiltonian that you write down associated with this model. Now it turns out that you can simulate this again in theory efficiently on a quantum computer. So this is now an entire class of algorithms that is being investigated. These are called variational quantum algorithms. These are, however, heuristics, which means we do not have a clear complexity result for this class of algorithms, right? It says that, well, any physical system will tend to its ground state. So if I map this optimization problem on this cost function, the cost function gets mapped to the lowest energy state of a physical system, then this physical system can be efficiently simulated on a quantum computer. Okay, so this is what is called, so there are algorithms that go by the name of variational quantum eigensolver. So people talk about solving the traveling salesman problem or knapsack problem using these kind of variational quantum eigensolvers. But like I said, heuristics. So that again is a question. Can one really make a complexity case using these kind of variational quantum algorithms? And these are also hybrid algorithms, right? Because they all the time require a classical feedback. So there is a school of thought that the way quantum computers are going to be used is not as standalone processors, but rather in conjunction with classical processors, especially to solve real-world problems using these kind of hybrid quantum classical algorithms. There are a few other applications that people do. For example, one of the papers that, one of the problems that my colleagues in IIT Madras work on is the protein folding problem from the biotech department. So you can map this problem of identifying configurations. Again, it's an energy, it's basically finding your way in an energy landscape. So any problem which involves this kind of an energy landscape and finding the minimum of the energy landscape can essentially be mapped to a Hamiltonian, which can be implemented presumably on a quantum computer. Yeah.
Thanks for a nice talk. Two questions. So regarding this desiderata that you mentioned for quantum, okay? So the decoherence seems to be one of the biggest issues in quantum. And so it is probably an unfair question, but is it more an engineering task or is there a clear mathematical problem that we haven't been able to, the problem in coding theory that we need to be addressed that we haven't solved, or is it more on the engineering side? I'm asking this more in the context of these, that each time Google releases something, Microsoft releases, they seem to be just an engineering sort of for this one. It doesn't seem to be answering a bunch of people. So what's the...
Yeah, nice. So actually, I would say it is both, all right? See, when quantum error correcting codes were developed, this whole stabilizer codes and all that, the sort of code that everyone thought we should implement is the so-called 7-qubit code or the Steele code, which comes from your 743 Hamming code, essentially. It's a quantum version of the Hamming code. However, it turns out that if you now add this layer of fault tolerance on top of that, which means so quantum error correction assumes that all your gate operations are ideal, right? But gate operations are noisy, encoding is noisy, measurements are noisy. Now, if you try to solve this problem of getting a fault tolerance threshold, which was one of the early calculations at Preston and so on, you found that that threshold number was very low. It was 10 to the minus 5. And then people developed topological codes. And then came the surface code about 10 years, 20 years later, where it brought down that requirement of physical error threshold all the way, I pushed it up to 10 to the minus 2. So now you can ask, are there codes where I can push this, the fault tolerance threshold is even higher? So in a way, there is an engineering challenge of increasing the coherence time. But there is also the theoretical challenge of can you design quantum codes, right? Where either because the encoding itself is so non-local, for example, that's where the quantum LDPC codes win out, right? Because they are now locally encodable, right? Or locally decodable. So for the 7-qubit code, for example, you needed to make this very non-local measurement, right? Which then was completely not fault tolerant. So to make that fault tolerant, you had to pump in many more resources. So that is a theoretical challenge. That can you come up, design quantum codes with high thresholds, local decodability, local, even your encoding being sort of like using sparse, encodings and so on. And there is the engineering challenge here. So it's both sides. Yeah.
You told about like the goal was to find the basis state of zero with equal to the set basis of plus. That was the goal. So you talk about interfering inferior superposition. So I was thinking, is the interference coming out of algorithm or it is initiated on its own?
So this in this algorithm that I was talking about, where I went from the 0 to the 0 plus 1 over root 2. So there is a physical process which does the interference there, right? Like, for example, if I was doing it with light, I would have a certain kind of crystal or a polarizer, which would essentially transform the 0 to a 0 plus 1. And I would put another polarizer at the end, which effectively performs that interference to go back to 0 or 1, depending on whether it was in phase or out of phase. Right? The plus is in phase and the minus is out of phase. So there are physical processes which implement these, what I call interference and so on. At the mathematical level, it's a matrix, right? It's a gate, right? Yeah. So these are ingredients that go into giving you the speed up, right? Because there is no speed up if you don't do the superposition or if you don't do that interference at the end, right? Because if I don't do that H gate at the end, I'm left with this joint state of the two registers where there is information about f of 0 and f of 1, but I don't know how to access that information. But once I do that H gate, that interference then says, okay, are these two in phase or out of phase? And depending on that, I get this answer about whether the function is constant or balanced. Yeah, it's a little, when you go through the details, maybe it becomes clearer, but yeah, this is the idea, because you still can't distinguish non-orthogonal states, like I said, right? And if you want to take advantage of the fact that you somehow have both pieces of information in your register, but you need to find a clever way of getting that information out, right? And that is where this H gate and so on help.
Maybe we can break and Prabha will be here. So if there are more questions, we can take that. But let's thank Prabha again for wonderful.
Thank you.
The other comment I want to mention, we do have a quantum for free. It's sort of a the physicists over here.
Yeah. Indeed.
In fact, one of the persons to contact is Jay, who is part of the lab, the Vijayana's lab, who's building the quantum computer.
Yeah.
Interested, you should.
Absolutely, yeah. We have a 7-qubit processor here. Yeah. And it's 6.
It's okay, easy.
What is
But I think it's, there's nothing.
But let's see what's set up.
But you have something else. Get this information. Very, so because you cannot prepare this thing,